Hello, I'm David. I'm the coordinator of the Maths Learning Centre, and I'm going to get out of shot now. And hello to you guys too, but that was for the benefit of the people watching online. It's a tradition now, several years, just having my face in here so that people know what I look like. Okay. So, it's summer semester 2020. And we're doing a revision seminar for Maths 1B. There's a whole lot of requests on the board, and I'm sure there are other requests in people's heads that they haven't asked. And I'll do my best to talk about whatever. What I am going to do is, for a while, I am not going to talk about Taylor series. The reason I'm going to do that, I'll probably still talk about it, but I don't want to start there because I talk about Taylor series every semester, and every one of those videos is on the Maths Learning Centre's webpage for Maths 1B, roughly in the order I think you should try them because of my perception of how good they are. So you can always go and look for that. So I don't want to start there. But maybe this year, if I do it later, it will be the best one ever, and I can delete some old ones, but it's just hard to talk about. So that's one of the reasons why we have a Maths Learning Centre, so that you can come and talk to someone in person and that sort of thing. Okay, so I would like to talk about something else first. So maybe I will just gauge the feel of the room about possibly beginning with eigen things and Markov chains. Got some serious nods there. I'm going to take your advice and do that. Okay, so when I lectured Maths 1A, Eigenvalues used to be in Maths 1A. When I lectured it more years ago than I care to mention, I remember being in a lecture theatre very similar to this one and writing on all the blackboards, everything you never wanted to know about eigenvalues, but you're going to be asked anyway, and turned out to be kind of cool. So eigen stuff, eigenvalues, eigenvectors, are my favoritist bit of Maths 1B. Though you might notice that I'll say that about other things as well. So, it's like having children and they can't, anyway, they're all my favorites. But eigenvalues probably are my actual favorites. And people have asked me, why do I think it's so cool? And it's not because it's useful. Like, I'm a pure mathematician. Usefulness doesn't come into my metric of coolness. Sometimes it does, but most of the time I don't care that much. It's more because, I don't know, it just sort of speaks to this whole everything is connected, everything's connected to everything else. And weird-ass ideas like eigenvalues tend to be connected to all these other things in surprising ways, and I think that's cool. I just think it's cool. And so you'll not get around me expressing that awe and wonder every so often as I do this. So be prepared. Okay, so I have a handout on the Maths Learning Centre website, actually. I really should put it here. I thought it was here. I better move it then. Okay. 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 Sorry, I will try and remember to put it on the Maths 1B page. I'm sorry it's not there. There's a copy of it in the Maths Learning Centre, and it's facts about eigenvalues, and it's a good place to start. Your lecture notes are, are fine, but not good for looking things up after the fact unless you've got them in an electronic form where you can search them. But flicking through your lecture notes to try and find the definitions is really hard unless you've highlighted them in specific colours. So what I've done is I put everything that I think about them here. So I will put them on these notes here as well, but I just wanted to run through this. If you've got an n by n matrix, it has to be a square matrix. An eigenvalue of A is a number lambda such that AV is lambda V for some non-zero vector V. So if you can find a vector that when you multiply the matrix by that, the vector matrix by that vector, it gives you the same answer as multiplying a number by that vector, that number is called an eigenvalue. Okay? It doesn't count if V is 0, because if V is 0, then A times 0 is 7 times 0, and it's 15 times 0, and it's minus 7,000 times 0, and it's a third times 0, and it's pi times 0. And so if 0 was allowed, every number is an eigenvalue, and that's stupid. Okay, so only non-zero vectors. And an eigenvector is a non-zero vector such that that happens for some lambda. So you can think about it in terms of the number, you can think about it in terms of the vector, but they both really need to be there in order for this thing to work. Okay. Cool. And then there's all these cool facts about there's some terminology, and then there's some theorems about how eigenvalues are connected to other bits and pieces of information around here. And then there's some classic problems that sort of illustrate how you would go about reasoning about eigen things. That's what this handout is. So I will just go like this. So I'll say that, and it will remind me to put it on the web page. Okay, so an eigenvalue is this. So an eigenvalue matrix A is a number lambda where AV is lambda V for some V not equal to 0. And that's an underlined 0 because it's a vector, so it has to be the 0 vector as opposed to just the number 0. Eigenvector of matrix A is a vector, a non-zero vector where AV is lambda V for some lambda. So let us look at the similarities and differences between these two things. So one of them is about a number and the other one's about a vector. They're similar because they both have the same equation in them. They're different because the vector's not allowed to be 0, but we make no comments about whether the lambda is allowed to be 0. And it is allowed to be 0. And stopping and having a look at how things are similar and different can help you notice the important details. So those are the definitions. So if someone asks you what's the definition of an eigenvalue, that is the definition. You can't just write AV equals lambda V. You have to put the whole sentence in that says which part of that is the eigenvalue. And same for vector. I believe it's not written quite this specifically in your notes. So. Okay, and then there's all these facts, right? So it turns out that there's this really clever way of figuring out what the eigenvalues are, and then the eigenvectors. Because the problem with this equation here is it has an unknown v and an unknown lambda, and so we have to simultaneously figure out an unknown vector and an unknown number, and that's tricky. So we need a way of trying to turn it into an equation that's only about one of those things at a time. And the really clever trick is that we turn it into an equation just about lambda. So that's the idea behind it. So, you know. How to find eigenvalues. So what we do is this. We go solve the equation lambda I, the determinant of the matrix lambda I minus A equals 0. That's how to find them. And the reason this works is, before I do that, just so you know, this bit, this thing, is called the characteristic equation. And this thing, without the equal to 0, is called the characteristic polynomial. Okay. So it doesn't matter which one you talk about, but it's important to note that if someone says characteristic polynomial, they just mean this thing here, not the equal to 0 part, just the expression with the lambdas in it. Yeah, but the characteristic equation is the bit that's equal to 0. So for the purposes of solving this, it doesn't matter if you do A minus lambda I or lambda I minus A. Excuse me. For the purposes of finding the eigenvalues, that doesn't make any difference because minuses are either wiped out or come out of determinants, and the 0, well, minus doesn't make a difference to that. So you're allowed to do A minus lambda I as well if you want, but if someone asks you for the characteristic polynomial, you must do lambda I minus A. Because the characteristic polynomial is supposed to begin with a positive lambda to the whatever. So that's just important. So you can do it the other way around. You just might have to minus it at the end to get it to the correct positives and negatives. So it's all well and good to have an algorithm, but it is very useful to know why the algorithm is the way it is. Partly because sometimes people ask you to prove these things, and partly because sometimes you forget the algorithm, and knowing a little bit about where it came from can help you to figure it out on the fly. So why this works if AV is equal to lambda V, then 0 is the same as lambda V minus AV. So what I've done is I've subtracted AV from both parts of this equation, and this is a vector. Like matrix times vector is a vector. So this is a vector, and when you subtract a vector from itself, you get the 0 vector. Okay, and I'm just going to write this round this way. And this is great, and when I solve normal equations with numbers, if I have two of the same number in there, one of the traditional ways of dealing with that is to factorize it so there's only one. And that would be great. Do not write this down yet. I'm going to need a bit of space. It'd be great. I could factorize out the v, except that doesn't make any sense now because I've got the number lambda minus the matrix A, which this object here is meaningless. Can't do number minus matrix. What does that even mean? So I need to find a way of being able to factorize this and so that the thing I leave behind in the brackets there is a real thing. And one way to deal with that is to say, well, this has got matrix times v. Can I write this as matrix times v as well? And I can, because any matrix, such as a column vector, times the identity is the same as what it was before. So this move just here, I have put the lambda, the v has been replaced with I times v because I times any vector is the same as the original vector. It's a very clever trick that allows me now to factorize, pull out the v, and leave behind in the brackets a matrix. Number times matrix is totally a thing. Minus matrix, still a matrix. Okay, so here's the really cool, clever bit of this process. We still have an equation that involves both a lambda and a v. It's still a problem. We have a number unknown and a vector unknown, which is a lot of unknowns. But if a matrix times a vector comes out to 0, that doesn't mean the matrix is 0. That doesn't mean that at all. And it doesn't mean the vector is 0. But if this matrix was invertible, it would mean the vector was 0. So, because if I could invert this matrix, I could times by the inverse, and I get v equals thing inverse times 0, which is that v is 0. So if this matrix was invertible, then the only solution would be that v is 0. But I want the ones where v isn't 0. I specified that right at the beginning, that my lambdas are the ones where the v isn't 0. So, if it's possible to go matrix times vector equals 0 without the vector being 0, that means the matrix is not invertible. So I'm just going to write that down one more time. If that was invertible, then the only solution is that v is 0. And I want v not to be 0. So we need lambda I minus a to not be invertible. All right? If it was invertible, the only solution would be v equals 0. We don't want v equals 0, so we don't want it invertible. And how do you tell if a matrix is invertible? Well, if its determinant is 0, then it's not invertible. So it's the coolest trick. It's so clever. So you know that big list of things you were taught probably in Maths 1A that relate all these big list of things that says when is a matrix invertible or not? We've just connected two of them together. A matrix is invertible when its determinant is 0, isn't invertible when its determinant is 0, and a matrix isn't invertible if when you multiply it by a vector you're able to get the answer 0 without that vector being 0. So that theorem back in Maths 1A, one of the reasons it's there is because eigenvalues are coming. There you go. Couldn't tell you that then because you didn't know what eigenvalues were, but that's one of the reasons it's there. And one of the reasons that theorem is there is so that we can do cool tricks like this. Okay, so that's why it works. We're able to, because of the virtue of invertible matrices, remove the v and just think about the lambda. So now we've got this equation and we solve that and we find the lambdas. Cool. So now the question is, how do you find the eigenvectors? So first, find the eigenvalues. And then second, for each eigenvalue, go back to this equation and sub in the eigenvalue and solve that. And we know how to solve a thing that is matrix times vector equals 0. That's the same as doing row operations on this. That sort of thing. You make an augmented matrix, row reduce it, chuck your free variables in, and ta-da. Okay. So it's good to know a process that you can follow that makes the thing appear that you're trying to look for. Yeah. So one thing I think is cool about eigen things is that it uses some of our things that we've seen before about how to solve problems with matrices. We're in a brand new situation that's a bit weird, but we've been able to turn our question into things that we know how to do, like row operations. That's the idea. I think it would probably be illustrative at this point to do an actual example of finding eigenvalues and eigenvectors so you can see the whole process. But I do want to say one more thing about this. One of the dangers of having an algorithm that produces the answer is always thinking you have to do the whole algorithm to produce the answer. So never forget, and this is really important, mathematicians think this way a lot and they write your exams, never forget that this is what an eigenvector and eigenvalue really is. Like if you can find a vector by whatever method you want that happens to do this trick, it's an eigenvector. This process here finds the eigenvectors, but it's not what eigenvectors are. So it's very common in places like 2-hour exams that are supposed to cover a 12-week subject or 6-week subject in the case of summer school, about 6 weeks double time. It's very common in an exam for lecturers to do part of it for you. So if your entire idea of eigen things is this whole process, then you're in the danger of having to do the whole process every time. And if the lecturer's done part of it for you, then that's a waste of time. So make sure you can notice when they've done some of it for you. Right, okay, just wanted something to say. So I'm going to do an example. And E-value and E-vector is short for eigenvalues and eigenvectors. Got enough stuff to do. Those 8 letters being removed just makes all the difference. Okay, so find the eigenvectors for the matrix. And I've got a really good matrix that I was looking at on the weekend. So I'm just going to just look it up. It is called D. It's not a diagonal matrix. I'm sorry, that's just the way it is. This matrix. 1, 2, minus 2 on the top row. Second row is 2, 1, minus 2. Third row is 2, 2, minus 3. This matrix is cool for all sorts of reasons. If I got rid of those minuses, it would be a symmetric matrix. But it's not a symmetric matrix because those minuses are there. So this one doesn't match that one, for example. The right size, but the wrong sign. Okay, cool. Okay. So, let's do it. Now, yeah, let's just do it. Let's find the eigenvalues, which means what we need to do is we need to find the determinant of lambda I minus d. So first I will write down what lambda I minus d is. And I find it easiest to first write down what minus d is. Okay, just switch all the signs in D. And then I have to add on lambda times I. So lambda times I is the identity matrix, but with lambdas down the diagonal instead. So when I add that on, everything off the diagonal is going to be the same, and I'm going to have to add some lambdas here. That's how I do it. So it's sort of a middle ground. Some people like to actually literally write the lambda I and the minus d. But I don't want to write too many matrices out in full. Okay, so that is the matrix lambda I minus d. And what I need to do is I need to find the determinant of that matrix. The determinant of that. Okay. Sweet. I'm just looking at the matrix now, and I'm thinking about ways to avoid having to calculate that determinant in full. You know, I could pick a row or a column and expand out along it, and that would be great. You know, I could totally do that. I'm in danger of losing lots of minus signs in that process. So I'd like to find a different way of doing it. And one thing I do know about matrices is that if I do row operations of the form row plus constant times row, then it doesn't change the determinant. And so if I do any of those to get more zeros into this, it might make it easier to figure out what to do. And I can also do column operations just as much as row operations if I'm working on determinants. And that works fine too. So for example, if I did row 2 minus row 3 minus row 2, I get a 0 here, and that might be helpful. Well, let's just work. Wait. Working on determinants here, David. So I didn't change row 1, and I didn't change row 2, and this minus that is 0, and this minus that, minus 2 minus minus 1 would be minus 2 plus 1, which is minus 1, and then minus lambda. And this minus that would be plus 1. That's great. It's looking good. And then I notice, do I, that this is a lambda plus 1 and this is a minus lambda plus 1. So they've both got a lambda plus 1 in it. And I know that if there's a multiple all the way through a single row of a matrix, I can pull it out of the determinant. This is an eigenvalue magic trick. Well, a determinant magic trick, but close enough. So if I saw a whole row of 2's, I could bring a 2 out of the determinant, and that works. But I saw a row with some lambda plus 1's. So this is minus lambda plus 1, and this is lambda plus 1, so I can pull them out. And this here, that might make my determinant much easier to do. Where? There. Well, minus 2. So I did this row minus this row. Minus 2 minus negative 1 is minus 2 plus 1, which is negative 1. Yeah. So already I know that one of the eigenvalues is going to be minus 1. Because I've got a lambda plus 1 here. Cool. Well, I could probably run through this now and try and figure out what the answer is going to be, but I really feel like doing one more operation just to show you that it's possible. Column 2 is going to be column 2 plus column 3. Sorry, did I say row operation? I meant column operation. Yes, because column operations like that don't change row operation, don't change determinants either. Whoop, sorry. So this plus that, I didn't change row column 3, and that plus that is 0, and that plus that is lambda plus 1, and that plus that is 0. It's looking good. So now if I do the determinant, I can expand it out along, say, the bottom row, because it's got lots of zeros in it. See, I just find this sort of thing fun. Admittedly, I don't have to do exams on it, so that does tend to make it more fun. So let's do the bottom row. Plus minus plus 0, minus 0, plus 1 times this determinant. And so I get lambda plus 1. And the determinant of this is lambda minus 1, lambda plus 1, minus 0, lambda plus 1, lambda minus 1, lambda plus 1. And my characteristic polynomial is neatly factorized already. I don't have to factorize it. Done for me. Maths lecturers have the tendency to choose matrices in their exams where at least one thing can be pulled out at some point. So that you don't have to factorize it from scratch. Worth knowing. That's about the psychology of maths lecturers, which is important to know if they're the people writing your exam. Okay. So what that means is that the eigenvalues are the zeros of this polynomial. So I can set it equal to 0 at this point, but I can also, just now that it's factorized, say that the eigenvalues are this. Lambda equals -1, and another -1, and a 1. There's a -1 from this one here. So -1, another -1, and a +1. So I've got 3 eigenvalues. 2 of them are -1. It's important to put them in as many times as they appear in these factors here. That's called multiplicity. You could say, if you wanted, that the multiplicity of -1 is 2, and the multiplicity of 1 is 1, if you wanted. So I think it was -1 multiplicity 2. Now I will use the whole word. Multiplicity 2 and 1 with if you wanted. Most people just write this. Yes?
He's listing the eigenvalues in ascending order.
So I'm going to repeat that for the recording. Is listing the eigenvalues in ascending order important? No, not at all. It's completely irrelevant. I will say that a computer will traditionally put them in descending order and have the biggest one first. That's just because of the way that computers go about finding eigenvalues, which is different to how we do it. Because the biggest eigenvalues have special properties, and so they'll tend to list the biggest one first. But the only reason that your lecturers ask you to list them in ascending order is to make it easier for the person or computer that's marking your work to find the answers in your working. So that's why. Okay. All right, but yes, it was just coincidence that I happened to list them in that order because that's sort of the order they were in. Okay, so I found the eigenvalues. And you'll notice it all worked neatly. But what this means is that somewhere there are some vectors that when I go a times vector, it's minus vector. And somewhere there are some vectors when I go a times vector, it's 1 times vector. Somewhere. And I need to find what those vectors are. They are the eigenvectors. So now I'm going to find the eigenvectors. Firstly, I'll do it for lambda equals -1. So let's see. So to do that, I need to solve this. -1 I minus a times v equals 0. I need to solve that equation. That's what I'm doing, which means I need to go back to here where I wrote down, it's not a, it's called d. That equation. I need to go back to here where I wrote down what lambda I minus d was and sub in -1 into that. So let's see, -1 minus 1 is -2. -1 minus 1 is -2. And -1 plus 3 is 2. So in a completely technical sense, there is a column of zeros here because I'm solving a system of equations, a matrix equation. And if you pay attention, you'll notice that all 3 of these rows are the same. And so if I did some row operations, I could get a whole lot of zeros there. So that's the reduced row echelon form. If you can just see it from the information that you have there, you are allowed to just write it down in an exam. So I notice that these 2 rows are the same as that one. That's going to give me rows of zeros. Divide this one by -1. That gives me the 1s in the positions. It's great. Okay, it's okay to do that if you can see it. And your lecturer's counting on it because you've only got 2 hours. Okay. All right. And so I would put in the free variables. And so I see that there's a good pivot column just here. And I could give a free variable to both this variable and that variable. So I would say something like x2 equals s and x3 equals t, and then x1 plus s minus t is 0, which means x1 is minus s plus t, And of course it went over to the next page. And so x1, x2, x3 is minus s plus t s t, which is s lots of minus 1, 1, 0, that's the s's, plus t lots of 1, 0, 1. Yay! So the eigenvectors for lambda equals -1 are s minus 1, 0, 1, 0, 1 for s and t not both 0. Because technically you're not allowed to have 0 as the answer. An eigenvector is not allowed to be the 0 vector, and if s and t are both 0, then it's not. Then it's the 0 vector, so it's not an eigenvector. There you go. So I've asked you what are the eigenvectors. This is your answer. If they ask you what are the eigenvectors, you have to have the s and t because they've asked you what are they, and you have to therefore list all of them. These are all the eigenvectors that go with lambda equals -1. If they just say, give a basis for the eigenspace, then you can just give a couple. Yes?
Some of the answers this semester had them in brackets with span.
Yep. Okay, so it's now time for me to mention another piece of terminology, which is eigenspace. Okay, so you both noticed something very important, is that there are times when you sort of have to have the s's and t's, and you've said span is an option, because if you've got s times something plus t times something, span is short for that. But technically span includes the 0 vector. So that's called an eigenspace. So I'm going to say two things. One is that when I come back to here, no. When you have matrix times vector equals 0, the solutions for V are always a subspace. Always. Matrix times vector equals 0, the solutions for the vector together are a subspace. That's one of the ways to define subspaces. Every subspace can be written that way if you want. And so the solutions to this are a subspace. But one of those vectors isn't technically an eigenvector. And so we want a word for that, and we call it an eigenspace. So just as an aside, the definition, the solutions to AV equals lambda V for some lambda are called the Eigenspace for lambda. That belongs to this matrix. And denoted E lambda. So I could say here, so the eigenspace for -1 is E -1, which is the span of these two vectors. Like that. Whoop, like that. So you're allowed to write it as a span if they wanted you to talk about eigenspaces and not eigenvectors. Yes?
Can you say that like S and T not be equal to 0?
Nope, I don't have to say that anymore, because the eigenspace is the solutions to this, which does include the 0 vector. And as long as everybody knows that every vector in the eigenspace is an eigenvector except the 0 vector, we're all okay. Okay? As long as we remember that we've included the 0 vector here, even though it's not technically an eigenvector, we'll all survive. And mathematicians are okay with that. Right. So if they ask for a basis for the eigenspace, you don't put the span in. So you say, basis for the eigenspace for -1 is that. So the point is that a basis is just a small number of vectors, and that when you wax span on it, it turns into the entire infinitely many vectors, which are the eigenspace. So one of the problems with any discipline where there's terminology is that you have to be able to answer questions for each of those terminologies. Happens in physics, happens in philosophy, happens in maths. So if you've asked for what are the eigenvectors, you must list them all. If you're asked for what's the eigenspace, you can say it's the span of something. Or you can say this, but allow S and T to be 0. And if you're asked for a basis for the eigenspace, it's just a couple of vectors, or however many there end up being. We're not even done yet, though. We've only done the eigenvectors that go with one of the eigenvalues, but there's another eigenvalue, so we're going to have to do that. For lambda equals 1, we need to solve 1I minus d v equals 0. So let's see, where's my matrix? 1 minus 1 is 0. 1 minus 1 is 0. And that's 4. You are allowed to leave off the column of zeros, but I do it to remind myself that it's actually a solution to some equations, because otherwise I forget that detail. This REF is going to be a little harder to just write down. But I do notice that this row plus this row is equal to that row. And so I can probably do this like that. So this is from row 2, this is from row 1, and this is row 3 minus row 1 minus row 2. Right. All right. You don't technically have to get to the REF, you just have to get to a point where you can figure out what the solutions are. But easiest from the REF. Okay, so I see two pivot columns. There's one here and one here. And so I've only got one free variable. And so I will say let x3 be t. And so then x2 is also t. And x1 is, well, if that goes over there, it'll be a plus, also t. And so x1, x2, x3 is t, 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 which is t times 1, 1, 1. So therefore, the eigenvectors for lambda equals 1 are t times 1, 1, 1. Oh, crap. Getting carried away. 1, 1, 1. With t not equal to 0. Now, that's not an underlined 0 because t is a number. Woohoo! And just for completeness' sake, eigenspace E1 is the span of 1, 1, 1. If you want, in an exam, don't answer all three of them. Just answer the one you've been asked. It's a waste of everybody's time to write them all down. Okay. So just to sum up at the end of this, what have we actually got? We've got that so the eigenvalues lambda equals -1 with E space. E -1 is the span of this. What was it? -1, 1, 0, 1, 0, 1. And lambda equals 1. Cool. Right. That gives all the information just summed up. Grammatically, it's not good though, so has. Yeah, okay. The with that would only make sense if it was a complement at the end of a sentence, and so these are really new sentences, so grammatically it has to be a has. Okay. Not that most people will care, but I care. But I'm not marking your exam, so good to know. Okay. So that's how you do it, and it's good to just take stock of what happened there. Always have to start by finding the eigenvalues. If you're going to do it this way, eigenvalues at the beginning, and whatever tricks you have for figuring out determinants are useful in this context. One of the reasons to show you how, back in Maths 1A, how row operations affect determinants is for this exact situation. Of course, actual matrices which have horribly decimal numbers in them, some other method. But, nice whole number matrices like this one, it tends to work very nicely. And it has to be factorized at some point. If it's not factorized already, you're going to have to factorize it. And that's why, especially for a 3x3, it's so useful to be able to do this trick here, where you notice that this row is a multiple of something and you pull it out. Okay. And then you have to do the matrix thing and the free variables to get the eigenvectors. Okay. So what does this actually mean for this matrix? What it means is that if I multiply this matrix by this vector, it will come out to a multiple of that. Yes?
The trick where you pull something out of a row, does that work if you've got a multiple each of a column or just the row?
Yes, it does. So the trick with the pulling out of a row also works for a column. And the reason is that when you transpose something, it doesn't make a difference to the determinant either. So anything you can do to rows, you're allowed to do to columns when you're finding a determinant. If you're solving systems of equations, no, doing things to columns just breaks everything. But determinants are allowed to do that. All right. So just I want to show you something. If you are in an exam and you have to do this, you should always do this last step just to be sure that you've done it right. If I go matrix times eigenvector, it should be the same as eigenvalue times eigenvector. So I'm just going to multiply it and see what happens. So minus 1 plus 2 is 1. All right. And minus 2 plus 1 is minus 1 and plus 0. 4. Minus 2 plus 2 is 0, plus 0 is still 0. And this is the same as minus 1 times the original vector that I multiplied by. So yes, it really is an eigenvector. And so my answer up there is correct. Show you a different way of multiplying this. This says that it will be 1 of the first column and 0 of the second column and 1 of the third column. That's what this says. And so if I go column 1 plus column 3, which is what this is telling me to do, I'll get minus 1, minus 1, minus 1, 0, minus 1. Which is indeed minus 1 times the vector I put in. So yes, it really is an eigenvector. And finally, 1, 1, 1 means you should add the 3 columns together. So when I add this together, I get 1. When I add this together, I get 1. When I add this together, I get 4 minus 3, which is also 1, which is 1 times 1, 1, 1. So yes, they really are all eigenvectors. I have done it correctly. There is absolutely no excuse if you have time to get eigenvectors wrong. I mean, you can get them wrong first. There's absolutely no excuse to have a final answer with eigenvectors wrong, because you can always tell if you've got your answer right. And people marking assignments and exams get extremely exasperated by students who get the final answer wrong, because they know you can always have checked your answer. I mean, there are many, many places to be wrong, right? Many places, because not least of which is a horrible determinant which has a million minuses in it. And any one of those minuses could go missing at any point, and you'd just get it wrong. And my things are out of order. There it is. So I would just keep an eye on your minuses. It's almost always true you'll lose some. And I've got another thing for you. If at this stage here your RREF turned out to have 3 pivots, which means that the only solution is the 0 vector, then either that means you've done your row operations wrong, or it means your eigenvalue isn't actually an eigenvalue. Because if it was an eigenvalue, there would be a non-zero answer for your V. So if here you get no free variables at this stage, you have definitely done something wrong. So never say that the eigenspace is the 0 vector or that 0 is an eigenvector. It is never true. So if your working seems to suggest that, then something is definitely wrong. I cannot stress that enough. Okay. This matrix, by the way, is very cool. If you get a Pythagorean triple, like a set of whole numbers that works in a right-angled triangle, like 3, 4, 5, and you multiply it by this matrix, you get another Pythagorean triple. Whoa! Unfortunately, this one causes the last term to be negative. There are better matrices than this one to do that trick. But this one has the neat property of having 2 differently sized eigenspaces, which is what I wanted to show you in this example. So also has the neat property that this matrix is its own inverse. If you multiply this matrix by itself, you get the identity, which is just awesome. Okay, right. So, cool. So how does this help with things like Markov chains, which was the thing that people asked about? So let me just go back to the screen. There's all these cool facts about eigenvalues. Like, it seems like such a weird-ass thing to do, other than just practicing your row operations and things like that. What it turns out is that all of these things that we have terminology for are related to each other. So a matrix has to have n eigenvalues. So as long as you include them according to their multiplicity, a 3 by 3 matrix has 3 eigenvalues, always, exactly 3, which is kind of cool. But this is like, there's so many eigenvectors, but there's only a small number of eigenvalues. And if you add them all up, it's the same answer as what you get when you add up the diagonal of A, which is just mind-boggling. This weird-ass process produces some numbers that add up to the same answer as just adding up the diagonal. I think that's so cool. And the product of them is the same as the determinant. Okay? And if you've got an eigenvalue, then the dimension of the eigenspace is at most the multiplicity. So we saw that when we got an eigenvalue with a multiplicity 2, then the eigenspace ended up with 2 basis vectors. And that generally happens, but it doesn't have to have 2. It's allowed to have less than that. And if you get 2 different eigenvectors that go with different eigenvalues, then they're linearly independent. And then the coefficients of the characteristic polynomial also can be built out of the eigenvalues. And if you sub a matrix into its own characteristic polynomial, like treat the lambda as a matrix and the constant as as constant times I, then you'll get the 0 matrix, which is one of my favorite theorems and is not the reason my daughter's name is Kaylee, but people think it is. My daughter's name is Kaylee because it means pure heart. But it's not unpleasant that her name sounds like one of the mathematicians involved in this theorem. And Hamilton is the guy who invented quaternions, which are the 4-dimensional version of the complex numbers. Yeah. And is ultimately the reason that we have multivariable calculus. So there you go. Okay, so they're all really closely connected, and I want to show you this example here. So I've got a matrix A, and it has those two eigenvectors. The little t is so that it's written as a column. It's currently written as a row. Both with eigenvalue 7, and its trace is 2. Find the determinant of A. So I haven't been told what the matrix is, but I have enough information to figure out what the determinant of A is from this information. So I know that A times 1, 2, 1 and A times 1, 1, 0 both come out to 7 times those original vectors because they're eigenvectors. And the trace is, which means, well, here we go. It's a 3 by 3 matrix. It has 3 eigenvalues in total. The eigenspace E7 contains both of those vectors, which are linearly independent, which means E7 must have dimension at least 2. Which means that the eigenvalue has to have multiplicity at least 2. Every time there's an extra vector in the eigenspace, an extra independent vector in the eigenspace, the multiplicity goes up by 1 at least. Okay, so the other eigenvalue is lambda, and for the trace, lambda plus 2 lots of 7 has to be 2, and so lambda has to be minus 12. And so they're the 3 eigenvalues, and the determinant has to be the product of the eigenvalues. Ta-da! We have enough information because of how the eigenvectors and eigenvalues are connected. And I used all of those theorems in this problem. I used the fact that an eigenspace has to have dimension at least as big as its multiplicity at least as big as its dimension. I used the fact that the eigenvalues, that there is exactly 3 eigenvalues for a 3 by 3 matrix. I used the fact that the eigenvalues add up to the trace, and I use the fact that the eigenvalues multiply to the determinant. This is a fabulous exam question because it uses all those theorems all at once, and this would make a maths lecturer extremely excited. Yes. So I would like people to ponder this for 10 seconds or so and give me some questions that a person could ask about this. Possibly you, but you just might be thinking of someone asking a question. So, give me a question that someone could ask about this problem and its solution. Oh, I seriously want one. Even if it's just a jumping off point from here to something new. What are we talking about? He says in a stage whisper.
No, just talking about how because the eigenvector entries.
Oh, I love it! Awesome. I didn't mention that. I hope someone would. Yeah, those vectors have 3 coordinates. The only way you're going to multiply by A is if A is a 3 by 3 matrix. Because I didn't tell you how big the matrix was. But that's the piece of information that told you how big it was. Awesome. Okay, that's enough of that one for the moment, unless someone had something. Cool. Okay. Cool. So, oh, these are the proofs. Oh, yay. This was, when I lectured this, I went and found some books in the Maths School of Maths staff library, and it had some cool old books, and yeah, there were some cool things. And the proof of the Cayley-Hamilton theorem is one of my favourites. It has these really cool magic tricks where, literally, it's nothing up my sleeve, and then everything disappears. Like, it's just so cool. But it's not the day for it today. Maybe after your exam, we can talk about the Cayley-Hamilton theorem's proof. So. The thing is that eigenvalues do this, vectors allow us to do this really cool trick, whereas if we make a matrix out of eigenvectors for another matrix, we can use that new matrix to diagonalize the old one. Or even better, okay, so here's an idea. This matrix has enough eigenvectors to make a basis for R3. So these two are independent, and they're guaranteed to be independent from that one because it's got a different eigenvalue. And so these three vectors together form a basis for R3 because they're independent and there's three of them. And if I can make R3 out of eigenvectors for A, then I can know what A does to any vector I want because it's made out of eigenvectors. So if Rn has a basis which is eigenvectors for A, and let's say it's like V1 up to Vn, with eigenvalues lambda 1 up to lambda n, then any vector in R3 can be figured out what A does to it like this. Then A times A1 V1 plus AN Vn, which is all the vectors in R3, or Rn in this case, is going to be A times lambda 1 V1 lambda n Vn. Because if I expand this out, I'll get A times V1, and A times V1 is just lambda times V1. So if I can make a basis out of eigenvectors, then it's sudden, and if I can write other vectors as combinations of those eigenvectors, then I can suddenly figure out what A does to everything without doing matrix multiplication and just doing number multiplication. And that's faster. And even better, not just faster, but also happens to allow us to figure out some really cool little proofs without actually doing any matrix multiplication at any point, or even figuring out what any vector is as a combination of these eigenvectors. So I just want to just give you a specific example of this trick in action. For the D from before, find D cubed times this vector. Just give me a second. Times this vector here. Okay. So the eigenvectors were, well, a basis of eigenvectors, right? Is minus 1, 1, 0 with eigenvalue negative 1, and 1, 0, 1 with eigenvalue negative 1, and 1, 1, 1 with eigenvalue 1. Okay? That was from our previous working. We got these are our eigenspaces here. Okay. And literally, you can just glue together the bases for the eigenspaces, and that's going to be a basis for the whole of R whatever. Okay, unless there's not enough of them, and then, well, sad. Yep?
How would you know which eigenvectors go which column?
Oh, which order to put these in? You can put them in whatever order you want. As long as later on you make sure that the values of lambda go in the same order as the vectors we're in to begin with, then it'll be okay. But it doesn't matter what order.
So any order doesn't really affect?
Yep. Any order. The reason why some people say do them in ascending order of the size of the eigenvalues is so that you don't have to remember what order you put them in if you always put them in that order. But nobody cares what order they're in. As long as the eigenvalues are in the same order as their matching eigenvectors, whatever order you like is best. Okay, and that was an excellent question. I strongly encourage people to ask lecturers questions of the flavour, how do you decide? Okay. So, if I can write this vector as a combination of these, then that'll be great. Oh, crap. Can I change the question? Oh, no, let's just do it. That's not the vector I was thinking of. Okay, so, looks tricky. I do not like it. So I'm going to change the question, I'm sorry. Every time I do this in a revision seminar, I say, wouldn't it be nice if you could in your exam change the question? I would prefer if the question was this. I did a third year course once where the lecturer had one number wrong and it made the question impossible. And so when someone came up and said, I think your question's impossible, she said, I changed the assignment question to, what does this number have to be in order for it to be possible? Okay. So a basis of eigenvectors is that. And I happen to notice that if I add these three vectors together, it's that vector. Let me just check that. Minus 1 plus 1 plus 1 is 1. 1 plus 0 plus 1 is 2. 0 plus 1 plus 1 is 2. Okay, cool. But if it wasn't so simple, you might have to work a bit harder than that. But usually if you're given something like this, it should be fairly straightforward. Of course, everything's straightforward when you've already got the answer. So for the lecturer, it's a little hard to tell sometimes if it's straightforward. But adding them together is always a good thing to try first. Okay, which means that A times D times 1, 2, 2 is D times minus 1, 1, 0 plus D times 1, 0, 1 plus D times 1, 1, 1, because that's how matrix multiplication works, and it works perfectly well with the D cubed as well. And I know that D times this is minus 1 times this. And D times this is minus 1 times this, and D times this is 1 times this. So D, so D times this is minus 1 times this, and if I times by D again, it'll times by another minus 1. If I times by D again, it'll times by another minus 1. D times this will times by minus 1. D times this again will times by another minus 1. D times this again will times by another minus 1. And same with this one, but this time the eigenvalue is 1. So this is going to be so minus 1 cubed is negative 1. And so I get, let's see, we've got 1, we've got 0, 0. Woohoo! So if it's easy enough to write a vector as a combination of eigenvectors, then doing any power of your matrix on that vector suddenly becomes much, much, much easier. Okay. I now know what the first column of D, the inverse of D cubed is. It's 1, 2, 2. So there you go. Of course, yep.
For the previous one, we had 1, 1, 2. We just try to find some constant state.
Yeah, let's do it. Let's do it. What? Okay. Okay. I would need to try to write this as a combination of them. So one way of doing that is to do some row operations with a matrix, but I just don't want to do that. That just seems like a waste of effort. I might as well just multiply by D cubed. Though to be fair, multiplying D cubed is not going to be very easy to do. Luckily for this matrix, d squared is I, so that's fun. Anyway, but we didn't know that yet because we haven't done it. So I guess if I did this minus that, that'd be 0, 0, 1. So this one so far, I need a 1, 1, 0. Right. These two together is 0, 2, 1. Oh, I don't like it. Oh, yes! This is exciting. So 2 of this plus 1 of this is minus 2 plus 1, which is negative 1. That's all right. Two of the middle one. Yep. Plus 1 of the first one. Is 2 minus 1, which is 1. Oh, it's beautiful. Well done. Aren't you clever? I should have, do you know what I should have done? I should have tried adding them all together in pairs before I did anything. Like I know when I add them all together, I get 1, 2, 2. When I add those two together, I get 1, 1, 2, 1, 2. When I add those two together, I get, 0, 1, 1. And going, oh, interesting. How far is 0, 1, 1 from the answer I have? It's 101 from the answer I have, which means I need 2 of that one. That would be a good strategy. I never like having an answer without trying to figure out if I can have a strategy for figuring it out in the future. Okay, and so A times 1, 1, D cubed times 1, 1, 2 is D cubed times 2 times 1, 0, 1 plus D cubed times minus 1, 1, 0. And the 2 can come out. So it's going to be 2 times minus 1 cubed plus 1. These both go with the negative 1, don't they? Do you know what this is going to be? Oh, this is so cool. We didn't need to do any of this crap. That's so cool. And watch what's going to happen. So this is minus 2 times 1, 0, 1 plus minus 1 times minus 1, 1, 0, which is minus 2 plus 1, which is negative 1, negative 1, negative 2, which is minus what we had before. It's an eigenvector. And do you know how I know it's an eigenvector? Without doing this, it's a combination of two eigenvectors that have the same eigenvalue. So since both of these have the eigenvalue negative 1, any combination of them has to as well, because they make an eigenspace. That's the point of eigenspaces. Any combination of eigenvectors with the same eigenvalue is a new eigenvector with that same eigenvalue. I didn't need to do any of this crap. Well, I mean, I had to do this bit. Didn't have to do that bit. I could have just, or 1, 1, 2 is in the eigenspace for negative 1. So d cubed times 1, 1, 2 is just going to be minus 1 cubed times 1, 1, 2. So cool. Ah, it's just awesome. Okay, there's always one of those things where it sometimes turns out to be one of those cool little tricks. It was one of the Maple TAs, I think, that went along the way of like, these are eigenvectors, explain why this one is. Or maybe it was a tute question or something. And you say, oh, it's a combination of those two. And so they're both the same eigenvalue, so this one has to be as well. If you combine two vectors with different eigenvalues, there's no way of knowing what's going on. But if they have the same eigenvalue, the new one is also an eigenvector with that eigenvalue. Okay, and why does this help us with Markov chains? Good question. And the answer is this. But I'm going to talk about Markov chains first. Does your lecturer call it Markov chain or Markov process? Good. Same deal. So Markov chain is a process that takes vectors, basically multiplies them by matrices, produces new vectors. That's called a dynamical system. Markov chains are a specific kind of dynamical system where the vectors represent probabilities or percentages to begin with. So the columns of the Markov chain matrix also represent probabilities or percentages. And so that's the idea. Percentages isn't a maths enough word. Proportions. Yep. So the matrix A, whose columns represent probabilities or proportions, and then it's used as a process to multiply by other matrices that have probabilities or produce vectors x. Does it normally start with x0 or x1? Does anyone know in your lecture notes? Goodo. Probabilities or proportions. And then you have that AX0 comes out to x1, and AX1 comes out to x2, and AX2 comes out to x3, etc. It's just a process where you pick a vector and you keep multiplying the A onto it to get the later ones. I don't know what the definition is. I'm sorry, this is what's in my head. You might have to look up the notes for the real definition, but this is what's going on. So in my head, Markov chains are networks where different objects are moving from one place to another within the network. And so in my head they go like this. There might be 3 things, and sometimes, and it's like an ant farm. Something like that. And what I imagine is you start off with some percentage of, you pour like 10,000 ants in here, and you start off with some percentage of them in each of these things. And then at every moment, there's a probability of them choosing one of these outward paths to walk to one of the other spots. And so you say, aha, well, we might have like 20% of them go this way, and 30% of them go this way, and 50% of them go this way. And so I imagine a little ant farm with a little thing, and the hole is wider in different ones, and so they choose to walk down different paths. And so 30% of whatever's here ends up over here, and then whatever percent of this ends up here, and so on. That's how I sort of think about them. So maybe this one has like this. Like that. And so you can imagine an ant standing here and going, all right, cool, I'm ready to go. Random choice, going to go one third of the time I'll go here. And then random choice, I'll go this way. And then random choice, I'll do it again. And random choice, I'll go back here. Random choice, I'll go this way. Random choice, I'll go this way. And as all of the ants choose randomly which direction to go at any moment, they all walk, and then you look at it and say, well, what percentage of them are in each corner at any moment? Those are the x's. So x naught is like how many percentage in number 1, percentage in number 2, the percentage in number 3, and then x1 is the same but after one step. And if I'd known I was going to talk about this, I would have brought my human Markov chain set so that you could be the ants and do this yourself. So if you ever want to do that, ask, because it's lots of fun. Yeah. Okay. Actually, just a second. That's me doing human Markov chains the first time. to sort of fuzzy out people's faces because they're high school students. Is there sound? There you go. And that's a fun activity. I've always wanted to do it on the maths lawns with like a drone from above. It'd be really cool. In my dream, I have a video series in the future like called The Maths Lawns, where I do maths things on the maths lawns. Okay. So the thing is, it's not really that at all. It's any situation in which there's a probability of, at any moment you can have a probability of it being in certain positions or certain states, and that it moves between them at certain times. And so the classic is weather, you know, where there's rain and sun, or just cloudy without rain, and there's a certain probability of that on each day, and then based on what happened yesterday, you can figure out what's going to happen today. And some of them are about, you know, what percentage of the population are of certain ages, and how that moves from year to year. Lots of things like that. And Markov chains also model a position that everyone is in like a literal board game at any moment. But you know, you can imagine snakes and ladders and having 100 squares, going, what probability are you of being on certain squares at certain stages in the game? And you can run through that too. It's just a really big matrix. Okay. And you know, economic situations are basically just games, and so it's the same idea. Okay. So what you have is that when you've got this transition thing, the idea is that if you put 100% of the ants in this spot here, then you're imagining having this matrix here. 100% in position 1, 0% in position 2, 0% in position 2. And this should give you, as your answer, what percentage everything is in afterwards. So if you follow that, 20% will still be in position 1, and 30% will end up in position 2, and 50% will end up in position 3. And so when I multiply a matrix by 1, 0, 0, it tells me what the first column is. And so the first column is this. Well, sorry, 3. % position 1, right? And what that means is that the second column will be the percentages that come out of 2 as well. If they're 100% in position 2, then 10% will end up here, 80% ends up here, and 10% ends up here. And so the second column is this. So I have extreme difficulty in figuring out what probability goes in which position in a transition matrix, it's called. And this is the only way I have to get it right every time. Other people have other strategies, but I mean, they go, oh, there's a from here and a to here. But I'm strongly dyslexic, and so having, like, not that strongly, strong enough, I'm strongly dyslexic with words that sound the same that are in positions. And so I can't tell left and right, so I have trouble telling which end is from and which end is to, because they're sort of just left and right. That's my issue. I mean, my twin brother is much more dyslexic than me, and there you go. But that's just enough to slow me down in an exam. So if I have a method I can use that doesn't require me to know which is left and which is right, then I'll be better. And that's this one. And so, just for completeness' sake, I won't actually draw all of this. This is just what's going on in my head. So 0.3 stayed in 3, 0.4 went to 1. All right. Okay, so what we get is that the matrix comes out to this. And there's some useful properties. Each column adds up to 1 because they're the probabilities of where individuals in a certain corner of the diagram go. Okay, so, rightio. The idea is that if you don't start with 100% of them in one corner, then what you have is, maybe you had 50% here, then 20% of the 50% will end up here, and 30% of the 50% will end up here, and 50% of the 50% will end up here. But simultaneously, 80% of the whatever percent are ending up here as well. And so all of those things end up together, and you get a new percentage there that's combined from all three of them, and the matrix multiplication will neatly just keep track of all of that all at once. And you don't have to worry about any of that. And that's why they're so cool, Markov chains. So, this is called a transition matrix. Okay, all right, so, doing really well. Transition matrices have really cool properties. By virtue of all of the columns adding up to 1, you are guaranteed for the number 1 to be an eigenvalue. Guaranteed for 1 to be an eigenvalue. That's really cool. You're also guaranteed for all of the other values for that to be the biggest eigenvalue. Closer to 0 than 1. It is possible that some of them will be negative, but they'll be like negative 0.2. It's got to be less than 1, like in terms of its size. So that's for transition matrices only, all right, for Markov chains. For a normal dynamical system, all bets are off and you can have whatever you want. Yep?
Do you mean closer to 0 than 1 or closer to 0 than 1 is?
Yeah, closer to 0 than 1 is. So i.e. the absolute value of lambda is less than 1. Yeah. Okay. So what that means is this. And you're also guaranteed to be able to... No, you're not guaranteed that. But anyway, if it's possible to write the whole of R3 or R whatever as a combination of eigenvectors for this matrix, then all the ones that are less... Just let me show you. It's an eigenvector basis for Rn, or R3 in this case. And with eigenvalues lambda 1, just 1 and lambda 2 and up to lambda n, because one of them has to be 1. Then A times any combination in fact, a to the power of k times any combination will be a1 a to the k v1 plus an a to the k vn, which would be a1 times 1 to the k v1 because it's an eigenvector, like that. And are you ready? One to the k is just 1. I'm just going to put the lambda 2 in. Are you ready? This number here, the absolute value is less than 1. All of these numbers, the absolute value is less than 1. If I do a number that's closer to 0 than 1 is, to a very high power, it will become 0. Like 0.2 to the power of a million is, well, it's already a fifth. You have 1 over 5 to the million. It'll be very small. And even if it's negative, it'll still be small. So all of these are going to be approximately 0 if k is big enough. And yep, fine. Right. So that means that if you start with any matrix vector at all and do A as many times as you can, you will always drift towards a multiple of the eigenvector for 1. And since you know that when you multiply a matrix whose probability, they're all probabilities, you'll always get one that's also probabilities. The answer is actually going to be a probability matrix as well, vector as well. So it'll actually get to just V1. It has to be a probability vector. Yay! So that is the magic of Markov chains and eigenvalues. I don't need to know what all the eigenvalues of a Markov chain transition matrix are, because the theory says that I don't need to know. I only need to know the eigenvector that goes with 1. And I don't even need to find any eigenvalues, because I am guaranteed for the number 1 to be one of the eigenvalues anyway. So the only thing I have to do if I have a transition matrix is find the eigenvector that goes with 1. And that eigenvector, that's where it's headed. If I keep doing this process with my ants walking around this thing over and over and over, they will eventually settle down to every time being almost exactly the same percentage in each corner. Even though percentages of these are moving out from every spot, it turns out that the ones that move out are matched by the ones that move in, and it stays roughly the same. Very similar to how equilibrium works in chemistry, if you've ever studied that before. Right. So they call this vector the steady state vector. Okay, it is sometimes possible, I think, but I'm not sure, I haven't studied this enough, that you can get 2 steady state vectors and then everything is thoroughly confusing. But usually there's only 1. Okay, so I'm going to show you how to find that steady state vector so that you can see how it works. And let's run with this matrix, and I really hope it's not bad. Okay. So I am guaranteed for lambda equals 1 to be an eigenvalue because the columns add up to 1. And the reason for that is that if I transpose the matrix and the rows add up to 1, I can multiply it by 1, 1, 1, and that will be an eigenvector. If the rows add up to 7, then 1, 1, 1 is an eigenvector as well. But the problem is that that's the transpose that I know what its eigenvector is. The transpose matrix has the same eigenvalues, but it has different eigenvectors. So I'm going to have to literally find it. But I am guaranteed, we know lambda equals 1 is an eigenvalue. We're going to find its eigenvectors. So 1i minus a. That's what we're going to have to solve. Okay, here we go. And so minus a is this. And I have to have 1 minus that. So if I'm very clever, and I was paying very close attention when I was doing this, I could go straight to writing this next one. So normally I wouldn't write both of these, I'd just skip straight to this one. Okay, so you are allowed to go straight to here if you can have the presence of mind to do so. Okay, I need to row reduce this. Of course I do. So I find that most of the time these are done in decimals that are at most 1 decimal place. Sometimes there's 2 decimal places. Either way, multiplying this by 10 or 100 would turn into something that doesn't have decimals in it. And so really it would be nicer if it was this. Okay. I don't like it. This makes me upset. This is what happens when you just make up crap. You get crap. Am I brave enough to try and do this row operations? Maybe. I can put a pivot here. There's some ones. Yep. Is it? Oh, how exciting. So this one plus that, these 2 is equal to -8, these 2 is -1, these 2 is -4. Awesome. I reckon that's always going to happen. Because they have to add up to 1, right? Ah, that's so cool. Like, and this one's minus these. We know that the original things add up to 1. Yes, this is awesome. We know that the original 3 add up to 1, and this one we replaced with 1 minus that. And so 1 minus this plus those 2 minus those 2 should add up to 0. Oh, that's so cool! Awesome! So it would be really good. So we could remove any one of these rows because any 2 of them add up to the other one. So we should remove the most annoying one, which would be this one. I don't know, maybe this one? I don't know. Which one's the most annoying? Yeah. 8. I'm going to remove this one. We'll do some row operations, right? Just believe that they're okay. Oh, I love it. So I just want to write this down here. Always the 3 rows add to 0. That's very nice. I love it. Okay. I reckon I can put a pivot here. I've got a pivot here already. Can add this onto that to put a 0 above it. That'll work, right? So this plus 2 of that would be minus 13. This plus 2 of that would be 0. This plus 2 of that would be 11. Sweet. Not what I was hoping for, but you know, great. Yay. Well, I guess I'm going to just have to do it in 11ths, in 13ths. Then row 2 is row 2 plus 5 of row 1. That'll be 0. That'll still be minus 1. And 7 plus 55 thirteenths. Fabulous. 7 would be... 7 times 13 would be 91. And minus 55/13 would be, so 90 minus 50 would be 41, minus 5 would be 36. Great. Ah, which is a whole number. No, it's not. That'd be 39. Crap. Oh well, it's worth a try. Okay.
30 or 31 over 13 or 30?
Here? Okay, so I've got my free variables now. There's a pivot there and a pivot there, and I have one free variable, so I shall call that t, my third variable. And so I'm going to get that x1, x2, x3 is t and 36/13 times t and 11/13 times t. And so I get that. It wasn't that painful. It's all right. Okay. And any multiple of this would be an eigenvector as well. So I'm just going to say that's equivalent to having 11, 36, and 13, multiplying everything by 13, because any multiple of that's an eigenvector too. So I just want to check if this actually really is an eigenvector to make sure I've done my working correctly. So I'm going to go back to my original matrix and multiply it by this and see what I get. So 2.2 plus 3.6. Just get a machine to do this for me. Plus 3.6 plus 5.2 is 11, and it's coming out to the correct first answer. Beautiful. And 0.3 times 36 plus 0.3 times 11 plus 0.8 times 36 plus 0.3 times 13 is 36. Okay, we're doing well. Okay, 0.5 times 11 is 5.5 plus 3.6 plus 3.9 is 13. Whew, it really is an eigenvector. Awesome. So just check. A times 11, 36, 13 is indeed 11, 36, 13. So it comes out to what it came to, so it really is an eigenvector. That's good. Now, the final step is that I'm not allowed to have this as an eigenvector because I have to choose my eigenvector to be something whose columns add up to 1. So I need to divide by something so the columns add up to 1. So the column currently adds up to whatever it does. If I divide by that, then it'll add up to 1. So total is 11 plus 36 plus 13, which is currently, let's see, that's 49, 50, 60. Cool. Okay. And so we're going to choose this vector. That's the steady state. And just for completeness' sake, I wouldn't mind figuring out what they were as percentages so that I felt better about it. Okay, so what this means is that when I run my little system, when I run my little system that I drew back here and stick in 10,000 ants, well, 100,000 ants, then run it for a while and let them walk around one step at a time, you know, open the gates and let them walk, open the gates, let them walk. Then eventually, roughly 18% will end up here, and 60% will end up here, and 22% will end up here. And that doesn't seem unreasonable. If 80% of the time, if you're in here, you stay here, you should end up with more in this corner than anything else. So that sort of makes sense. Yeah. But there you go. And so that's the steady state vector. So I guess the final thing for this. So that means that long term, the probability of this, if this was not ants, but the state of the probabilities of something happening like weather, you're saying in the future, the general probability of having weather state number 1 is 18%. Yeah. There you go. So you thought we were going to diagonalize things, but we didn't. Now, my recording still has some number of minutes that it's not telling me how many there are. I don't know when my recording's going to turn off. So, sorry? Well, I gave myself an hour and a half from when I started, just in case, because you never know. Yeah. So, I think it would be good for someone to ask a question about this or anything else. Yep.
Are we expected to know how to do all that in the span of
I don't know.
that seems really
Yes. Look, classic exam questions will tend to do part of the working for you. So they might give you some information about how the probabilities work and say, write down the standard matrix, the transition matrix. And then they might say, find the steady state vector. And then in brackets down the bottom it say, it may help to know that the reduced row echelon form of this matrix is this. So they might say, the reduced row echelon form of this matrix is this. And until you wrote down the standard matrix, you wouldn't know that that was relevant at all. So they might just tell you what the reduced row echelon form is without you having to do it yourself. That's the sort of thing that they might do. Or they might say, write down the standard matrix. Now, here is a vector. Is it the steady state vector? And all you would have to do is multiply it by the matrix to see if it was an eigenvector that went with 1. That's the sort of thing they'd ask. So they don't necessarily ask you to do the whole process, but they need you to know enough about how the process works to be able to do just the last bit or the first bit. Does that answer the question? Yeah, I never know what they're... Like, people come to me afterwards, so they're licking their wounds after their exam, and they go, oh, they did this thing. I say, yeah, but you didn't have to do all that. You had to do this. Yes?
Would 1 be multiplicity 3 in transition matrices because it's the eigenvector, it's eigenvalue for each vector?
Well, the individual so the question was, is 1 multiplicity 3 because each of the 3 rows, columns add up to 1? And the answer is no, because the only reason, there's 2 reasons, is that individual vectors don't have none of those vectors are actually eigenvectors for the matrix. Because even though they add up to 1, you don't multiply them by the matrix to get them to add up to something. And secondly, that adding up is actually telling you about the eigenvectors of the transpose matrix. And so the matrix you have has been transposed from that situation, and so it just doesn't tell you anything. Yeah. Yep?
How much should we know about the Runge-Kutta method?
I don't know how much you should know about the Runge-Kutta method for your exam. When I look at your notes, you don't get much information about the Runge-Kutta method. And as far as I can tell, all they give you is to say, it's sort of like Euler's method, but more. And the only difference is you make this small change to the MATLAB code and it does it. So as far as I can tell, you just need to know what its purpose is, which is to find numerical solutions to differential equations, and know how to read what the MATLAB might tell you. Yep.
help.
Yep.
It's like you don't need to know the MATLAB, but you do need to know what it's used for, but they don't actually mention that.
Okay. So cool. My instincts are good. So if they say you don't have to know the MATLAB, in that case, you just have to know what it's used for. So if they said with 6 steps of the Runge-Kutta method, the answer was 6.3104, and you would say, okay, what that means is that y of 4 is 6.104, something like that. Yeah, you have to know that it comes in steps like Euler's method does. And so that's my guess. But my other guess is that most lecturers just won't include it at all. That's my theory, but I never know for sure. Yep?
So, from what you drew before, the Markov chains are just a form of directed graph. Is that what you
Yeah, they're a directed graph with weighted edges.
Okay.
So there's a weight on each edge that says how likely it is to go along that path.
Yeah. So then the transition matrix is like the adjacency matrix of that?
Basically, but you put the weights in, instead of a 1 when they're connected, you put whatever numbers on that line.
Okay. And then I'm just trying to think of how because in maths when it was when you take powers of the adjacency matrix, you get the number of
Paths.
paths with the different walk lengths.
Right, this is excellent stuff. Trying to connect it to something you've seen before is a great strategy. So it's almost like you could imagine that this point 2 is actually 20 paths that go from here to here. And this is actually 30 paths or 80 paths. And so in the network thing, what were they called? The networks, I call it, but there's another, graphs. In the directed graph thing, the adjacency matrix, when you told you how many paths there were from here to here in one step, and then the adjacency matrix squared told you how many paths there were from here to here in 2 steps, and that sort of thing. It's the same thing, except that the Markov chain matrix tells you probabilities of going from one to the other. So it's not surefire, it's just a probability. And so we're saying that there's a 20% chance of going from here to here. If you multiply the matrix and you look in position 1, 3 of the matrix, that tells, so if you've got the transition a to the 4, let me just write this down. So a to the 4, position like 1, 3, right, tells you the probability of going from 1 to 3 in 4 steps. So back with the adjacency matrices of graphs, it told you the number of paths that go from 1 to 3 that are 4 steps long, right? And now this is saying the percentage, like the percentage of paths that go from one to the other in 4 steps. It's the same idea. Yeah, tells you the same thing. So compare to adjacency for like a directed graph, and where a to the 4 position 1, 3 was the number of paths from 1 to 3 in 4 steps. Yeah. So that's the comparison between those things. And it's the same idea, it's just that we're allowed to have numbers other than 1 in those positions. Yeah. So it's like fuzzy directed graphs. It's a little bit like selection in something like Photoshop, where you can select a cell to colour it in, and you can like 20% select it, so that you sort of colour it in 20% grey, that sort of thing. Yeah, so if you're ever interested in looking up fuzzy mathematics, it's the idea of where you would do the things you would normally do with zeros and ones, and you replace them with probabilities instead. So that's basically what we're doing. Yeah. All right, we're doing well. We're on a roll. All right, cool. I am going to do one more thing. but not about this, unless someone has something about this, because it's nice to round them all off together. Cool. So there are other lectures that talk about the rest of Eigen stuff, and there are other worked examples. I just told you enough to get to the point of being able to do this thing. So on a completely other note, Taylor series, everyone asks me every year about this thing, and I do not have time to talk about the whole thing because it's just complicated. But the idea of Taylor series is rewriting functions as polynomials. And I want to talk specifically about the Binomial Theorem because most people don't get it, and I didn't get it, and I want to just talk about it. So since I'm here, I will not be offended if you have to go. Okay. So the point of a Taylor series, like the point of a Taylor polynomial, is to approximate your function as a polynomial. So I'm just going to say this bit first and then I'll move right. So the idea is that polynomials are nice. They're easy to differentiate, they're easy to integrate. We know how many turning points they're supposed to have. They're nice and smooth. If you see one that's like degree 7, you go, oh, it's probably going to have this many wiggles in it. They're really nice and they're easy to figure out what to do. They're very easy to teach a calculator to calculate them. They're just nice. But the problem is, most functions aren't polynomials. Which is sad, right? Square root, perfectly good function, not a polynomial. Sine, perfectly good function, not a polynomial. Ln, perfectly good function, not a polynomial. And they're all functions we really want to know about. Okay, there we go. So there are two solutions to this problem. Solution one is approximate them with a polynomial. Find a polynomial that's close enough. And that's what Taylor polynomials are for. Solution two is create a new kind of thing which is like a polynomial, but isn't, which is Taylor series. Make up infinite polynomials instead, and that's Taylor series. And those are our two solutions to the problem that for polynomials are nice, but functions aren't polynomials. And so Taylor polynomials are like, oh, cool, I think degree 5, that'd be nice. I like degree 5 polynomials, and I'm going to create a degree 5 polynomial that's close enough. Though you should know in practice, most people just use degree 1 polynomials, Taylor series. Possibly 2, if it's a stretch. But this one is a whole different thing. This one is like a theoretical mathematics, theory idea, which is saying, yeah, but sure I could go degree 5, but it's not equal to sine x. What if I went forever? And then it would be equal. We're used to that sort of thing. Like 0.3 is not a third. And 0.33 is not a third. And 0.333 is not a third. And 0.3333 is not a third. And none of those numbers are a third if you stop. But if you go forever, then it's a third. That's the idea of Taylor series. Okay? E to the x is not 1. It's also not 1 plus x. And it's also not 1 plus x squared on 2. And it's also not 1 plus x squared on 2 plus x cubed on 6. And it's also not 1 plus x squared on 2 plus x cubed on 6 plus x to the 4 on 24. But if I did that forever, then it would be equal. Okay. And why is that useful? Well, it's useful because if you have that thing written down already, you can already find the Taylor polynomial without doing all the annoying derivatives. That's one of the reasons it's useful. It turns out that solution 2 can give you the answer to solution 1. Turns out. So if you find other ways to figure out solution 2 than the traditional one, then it can give you the answer to solution 1. That's very nice. Okay, so that's enough of that. That's just a general idea. So what we would like is for every function to have a Taylor series. Not all of them do, but lots of them do. And if we can remember a few of them, then we can figure out things without having to do all the annoying derivatives. And so the classics are these. That one, e to the power of x is the sum from n equals 0 to infinity of x to the n over n factorial. So this is short for this, right? 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus forever. But the point is that you don't have to go forever to be able for it to be quite accurate for quite a lot of numbers x. I mean, the closer x is to 0, the more accurate it is. But if you wanted this to be accurate to 3 decimal places when x was 2, you just need to have enough of these and then you can stop. Okay, and sine and cos are nice. Sorry, it's a minus. So with cos, you only have the even-powered ones from e to the x, and they switch between plus and minus. So cos is an even function, which means its Taylor series will only have even powers. These are technically Maclaurin series, Taylor series with center 0. So only even, and they switch between plus and minus, and the shorthand way of writing that is usually, yes. Yes, that should be a minus there. Is like that. So x to the 2n over 2n factorial, the 2 makes it even, and then the minus 1 to the n switches between the plus and the minus. And sine x is x minus x cubed on 3 factorial plus x to the 5 on 5 factorial minus x to the 7 on 7 factorial plus and so on. The odd ones from e to the x switching between plus and minus, and that's two n plus 1. Because if you do an even number like 2n and then add 1, it's an odd number. They're the classics. There is a couple that you've seen before. There is this one. Like that. 1 over 1 minus x is that. But it only works if the absolute value of x is less than 1. The edx, cos x, and sin x, they always work no matter what. But these ones, only if x is less than 1. And they're the classics. They're our classic Taylor series that you're supposed to know the answers to. This one, you know better as the geometric series, you know it the other way around. And there is one more that they teach you in Maths 1B, which is mildly puzzling. And it goes, it's called the Binomial Series. So, the binomial series is written this way, and this way is puzzling, and I'm going to write it anyway, and we're going to talk about it. Okay, 1 plus x all to the power of k is 1 plus the sum from n equals 1 to infinity of k choose n times x to the power of n. Sweet. So, right. Before you saw the binomial series, how many people had seen this notation before? This k choose n thing before? That is combinations? Yep, okay, cool. They mentioned it at least once in Maths 1A when you were doing slack variables. Puzzled strangely. Okay, so what it means there when you first saw it in Maths 1A, or if you saw it elsewhere in the world, you've probably seen it as this in the past. I don't want to write it, but like NC, KCN or something like that. You've probably seen it like that. That's what a calculator calls it. What it meant back in those days was the number of ways to choose n things out of k things. That's what it used to mean. So, k choose n used to mean the number of ways to choose n things out of k things. Okay, that's what it used to mean. It does not mean that anymore, I'm sorry, in the binomial theorem. It does mean it in the specific case where k and n are both whole numbers, like natural numbers. Then yes, it does mean that. And the reason it means that I will get to in a minute. What it means now is something else entirely. So it used to mean this. Now it means this. So you start with n, and you keep multiplying by numbers less than n until you get down to 1. That's what you put on the bottom of the fraction. And on the top of the fraction, you start with k, and you keep multiplying by numbers less until you end up with the same number that you have on the bottom. This is what k choose n means in this formula. This is how you would figure out k choose n in this situation, and we copied the same formula, but now we're going to apply it to other things. It will make most sense if you see it with examples. So, 13 choose 3, 3 times 2 times 1 on the bottom, that's 3 factorial. And then on the top you have 13 times 12 times 11, and then you stop because there's 3 terms on the top and there were 3 terms on the bottom. And that's the answer, whatever that number is, which is whatever 13 times 11 times 2 is. 13 times 11 is 143 times 2 is 286. Okay. Are you ready? 1 choose 3. So we have one object and we want to choose 3 of them. Cool. So we'll go 3 times 2 times 1. 1 times 0 times negative 1, so the answer is 0. Sorry. So 3 times 2 times 1 on the bottom because of the 3, and then the 1 times 1 number less times 1 number less on the top, so the answer is 0. Which is what you would expect. There are no ways to choose 3 out of one thing. Are you ready? Ready? Here we go. Minus 1 choose 3. 3 times 2 times 1 minus 1 times minus 2 times minus 3. Because we started 1 and we went down 1 and we went down 1 again. And there's the 3 things here and there's 3 things there. That's how it works. So the answer is negative 1. So the number of ways to choose 3 things out of minus 1 things is negative 1, which makes no sense, and that's why this doesn't mean the number of ways to choose things out of things anymore. All we've done is copy the formula that we would use when we were doing choose on new numbers. Yep?
Does that mean when you use the original meaning, you don't use negatives?
Sorry?
Do you avoid negatives when you use choose in the original context?
In the original context, it only applies to numbers where this number is bigger than this number. And so it doesn't matter. So negative numbers don't appear when you're using it in the original context, so nobody even wondered about that. Yep? Yes, bottom number has to be a whole number. Top number can be anything you like. So one more, just to really drive. A half, choose 3. So 3 times 2 times 1. A half, we take 1, we get negative a half. We take another one, we get negative 1.5. And I stop because I'm at to the end of this one. If it was choose 4, there'd be 4 of them. And so I get, interesting. So I get 3 over 8. So 3 over 48. Yay! 48 is a multiple of 3, actually. That cancels with that out, so that'll be actually 1 over 16. But a half choose 4 will be negative, because there will be 4 times 3 times 2 times 1, and a half minus 3 over 2 minus 5 over 2. Okay, so cool. Right, so what we've done is we've repurposed an old symbol that we used to use for choosing in probability situations, and we've said the calculation we would do in that situation that always gives the right answer is this calculation, and we'll just apply it to having numbers in k position other than we used to have. Okay. Cool. So, right. The specific question I was asked, I took a photo of it, so just give me a second. Find a Taylor series for f of x is 1 plus 2x to the third up to the x squared term. Okay, I'm going to rub that out and write it because at the moment it's 1 over squiggle. Right. So the binomial expansion says that 1 plus 2x to the third, if it was just an x, it would be 1 plus the sum from n equals 1 to infinity of x, of 1/3 choose n times x to the n. That's what it would be if it was just an x. Since it's a 2x, it will be that. So just what that means is that when n is 1, I get 1/3 choose 1, 2x to the 1. And when n is 2, I get 1/3 choose 2, 2x to the 2, plus forever. But we were only asked to do it up to the squared term anyway, so we're going to stop there. Okay, so 1/3 choose 1 is 1 on the bottom. If it was 2, it would be 2 times 1. If it would be 3, it would be 3 times 2 times 1. And this number on the top, Going down the same number of steps, well, there's no other steps. So that's what it is. And 1/3 choose 2 is 2 times 1 on the bottom and 1/3, and then what I get when I do subtract 1 from that, which is minus 2/3. So I get 1 plus 2/3 of x plus, so that 2 cancels with, oh no, crap, just a second. That's minus a ninth there, all of this, times 4x squared. So that's 1 plus 2/3 of x minus 4/9 of x squared plus forever, and I'll stop there. Because that's what I was told to do in the original question. Now, for the purposes of me learning stuff, I may want to go further. But for the purposes of answering an exam question, I would stop. So, ask me something about the binomial series. This thing?
Yeah.
Yes?
If that was like a 4 plus 2x to the third, would that be 4 plus the sum of?
Ah, that is a very good question. Let us consider that. Okay? So, you're just saying, what would happen if like that? Oh, sorry. I normally shift it at the bottom and it's a problem, but now to the top. I can have a problem at both ends. It's like having gastro. Sorry. Sorry, not sorry. So, and you're saying, does this formula turn out to have a 4 in this spot here? And the answer is no, unfortunately no. The formula only applies to things that have a 1 in this spot. So, like that. Like that. And now I have something that does have a 1 in the right spot. And so I would go, well, that's 4 to the third times 1 plus a half plus a third choose 1, because that's from the power, times a half of x to the 1 plus a third choose 2 times a half of x squared plus, and so on forever. Because I asked for a Taylor series, and so I have to expand it out. So we've got a cube root of 4 plus a cube root of 4 times a third times a half of x plus the cube root of 4 times a third times minus 2/3 over 2 times 1 times a quarter of x squared. Oh wow, it's bad. Well, it wasn't going to be pretty, was it, really? So what have we got? We've got a minus, we've got a 2 and a 2. They cancel. We've got a 9. We've got 1 over 4 times 9, 36. That does leave us with having to calculate what the cube root of 4 is, but that's all right. I mean, it's not really. If I were Newton in this situation, I would go, what the hell are you doing to me? I'll just run off and do my other Taylor series just for that other one. Yeah, so if it's not a 1, you're going to have to make it a 1. That's the answer to the question, really. What is your name? How do you spell your name?
M-E-L-A-R.
You've told me this before.
Yeah,
So M-E-L, yep.
A-R-N.
Beautiful. Just going to pop this on the what if wall in the Maths Learning Centre, which says, because I think what if questions are really important questions. Okay. Even if they're just what would happen if this number was different. Yep.
So binomial series is divergent.
Yes, actually, that's very important. Only applies if the size of x is less than 1.
And if it's not,
Then it's not equal to that because it's divergent.
so it will be convergent if x is less than 1.
Yep. Well, it's convergent if x is less than 1. It's also convergent for any x if k is a whole number. Because if k is a whole number, when you get past k, you end up with a 0 for that coefficient, and so it all works out fine.
So that's absolute value.
Yep, it'll work if x is negative, as long as the negative number is less than 1. Good. Excellent. Yeah, I think the binomial series is really cool, and I think I have time to explain where it comes from. So there are 2 reasons it comes from. One is really cool, and the other one's just, oh, really? Okay. Okay, so the first reason is if this was a whole number, yep, then this is like 1 plus x and 1 plus x up to 1 plus x, and there's k of them, right? And when you expand this out, to get a 1, like to get the constant term, then like you have to multiply everything in this with everything in this, and then from the answer to that, everything in that to everything in the next one, and so on. So ultimately, you have to multiply everything in each of these with everything in each of the others. And so what that means is you have to take all of these and go, well, when I multiply them all out, I'll have to pick the 1 or the x from each of them. And so if I want the 1, the constant term is going to be 1, because that's going to be choosing the 1 from each of these. And then the coefficient of x here, I've got k factors. To get an x, I'm going to have most of them have to be 1s, and one of them has to be an x. So I'm going to have to choose a 1 from most and an x from one of them. So the number of ways to get an x, when I expand this out, will be the number of ways there are to pick one of these factors to have an x, and the rest have 1s. So there's k factors, and I need one of them to have the x. And to get the x squared, I'm going to need to choose 2 of them to have an x, and all the rest to have 1s. So that's going to be that many choose 2. 2 from, choose a 1 from most, and an x from 2. And so on. Yay! Okay. And that's why you would expect there to be choosers when you expand out a binomial. And the way that to calculate a choose, you could say, well, there are k factorial ways to arrange. So if you have, if you want to know how to choose 2 things out of k, then you could go, well, just a second. Oh, crap, just a second. The first one, there's k ways to choose which one is the first one. Which of these k? There's k choices for the first one. And then once you've chosen one, there's k minus 1 choices for the next one. So you times them together, k times k minus 1. And once you've chosen 2 of them, there's k minus 3, 2 ways to choose the rest, and so on. And you choose that as how many there are. But it doesn't matter what order you pick them in, and so you need to divide by the number of ways there are to order those things, which is the bottom number factorial. So that's the argument for why that works. But of course, this is stupid. How do you have half? If you put a half here, how do you have, like, or a third? How do you have a third of a factor? It doesn't make any sense. All right. I watch closely. If I wanted to make the Taylor series, I would need all the derivatives, and I have to sub them in and divide by the factorial and times by the x to the whatever and add them up. That's how you do a Taylor series. So when I do the first derivative, I'll get k times 1 plus x to the k minus 1. And when I do the second derivative, I'll get k times k minus 1 times 1 plus x to the k minus 2. And when I do the third derivative, I'll do k times k minus 1, k minus 2, 1 plus x to the k minus 3, and so on. And so f of 0 is 1 plus 0 to the k, which is 1. And f dashed of 0 is k times 1 plus 0 to the k minus 1, which is k. And f double dashed of 0 is k times k minus 1 times 1 plus 0 to the k minus 2, which is k times k minus 1. And f triple dashed of 0 is k times k minus 1 times k minus 2 times 1 plus 0 to the k minus 3, which is k times k minus 1 times k minus 2. And so when you make the Taylor series, it will be each of these divided by their matching factorial multiplied by the x, right? And so my Taylor series 1 plus k times x over 1 factorial plus k times k minus 1 over 2 factorial times x squared plus k times k minus 1 k minus 2 over 3 factorial x cubed, etc. And this is the same calculation we do to do k choose 3 when k is a whole number. And so I'll just do it when k is a half because that's what the derivatives tell me I have to do. I told you it was unsatisfying. Yeah. So basically, the magic of derivatives and the way that they are related to factorials tells you that when you do the Taylor series, you get the same answer in this position as you would when you did your probability counting reasoning over here. And so since this works when k is a half, because it's just derivatives, I'm going to borrow the notation for what was this here and use that notation for this. But it's literally just a shortcut for all of the derivative things you do when you do differentiate this thing. When you differentiate something with a power, you're going to multiple times, you're just going to multiply by successively smaller powers. And that's it. It's not special at all. And sometimes the wonder of mathematics is that things are less special than they seem. Yeah. But I think it's cute that mathematicians said, well, I'm just going to borrow the notation I use for the other thing and call it choose, because that sounds stupid and silly. But it's just a shortcut for doing the stuff that the derivatives do without having to do them. Yeah. There you go. And that my thing is flashing, which means I am going to finish. The recording is going to finish shortly. Don't forget, Maths Learning Centre is open this afternoon and tomorrow afternoon. And if you're desperate, Thursday afternoon, starting at 12. But you would have to be a certain kind of desperation. But we will treat you nicely if you come in on Thursday, give you a cup of tea. Thank you.